I think this part you already know. That is the opposite polarity device of the NPN transistor. This is the collector, base, emitter, and the physical construction of this looks something like this. I mean, this is not a planar device. Okay. On an IC, this is not how a device will look, but this is the usual representation that is used, NP and N, right. This is the base, emitter and collector, and this is equivalent to the qualitatively equivalent to the NMOS transistor. Okay. And similarly, there is what is known as a Pnp transistor. You have seen this, right? Have you seen it in the devices course? Pnp transistor. Yeah. So, all you do is interchange P and N. So, you have N type base, this is the base, collector and emitter, and I am drawing the emitter on top, keeping with my convention of putting the higher voltage on top and lower voltage on the bottom. So, we have VEB here and VEC. The current is primarily dependent on VEB and slightly dependent on VEC, and this is equivalent to the PMOS transistor. Okay. And the collector current flows out of the collector just like the drain current flows out of the drain. Okay. So, you use it just like you do the PMOS transistor, and just like with NMOS transistor, this IC is an exponential function of VEB. And it has a slight linear dependence on VEC. Okay. Now, just like also with the NPN transistor, what you do is, for hand calculations, you assume that VEB is 0.7 volts when it is on, or some fixed voltage that is given to you. Okay. Yeah, it will be outside. So, everything will be opposite. Okay. So, if this is IC, this current will be IC by beta, and this current will be IC times beta plus 1 by beta. Okay. So, in case of NPN transistors, I think you know this. So, electrons are injected into the base and then they shoot into the collector, and similarly in case of PNP, electrons shoot from holes shoot from emitter to the base and then they also go through to the collector. Okay. So, the question he was asking, I mean, we can make a CMOS inverter like this. This is the basis for all the CMOS gates. Okay. If you want gates with more inputs, each of this PMOS will be replaced by parallel or series combination of PMOS, and NMOS will be replaced by parallel or series combination of NMOS. Okay. So, essentially based on this you can make any logic gate that you want. Okay. That is another advantage, you do not need multiple stages. Like let us say you want to realize a function like A times B or C, you can do it with a single stage with some exception. Maybe you will be able to realize the inverted form of this. So, you have to have a CMOS inverter following that, but besides that you can realize all logic functions with a single stage. That is not so with bipolar, and you also cannot make this with bipolar. So, let us say we try to mimic that. Could we do this, or why could we not do this? Okay, let us say that is fine, meaning the previous gate can drive whatever current is required. Base current? No, I mean if I leave it like this, if I just realize the circuit, it has to be right by Kirchhoff's current law. That current has to be equal to that current. The transistor has to move into the right region of operation for that to happen. Okay. I mean, you can't really make this because, first of all, I mean, forget the digital gate for a moment. Imagine the self-biased case. Okay. So, in the self-biased CMOS, what was the dependence of this current on the supply voltage? So, it was VDD minus some sum of threshold voltages square. What do you guess it will be here? No, why will it be square? It will be exponentially related to VCC. So, you just cannot use this. Okay. So, the current will be completely out of control. The same thing will happen here. What happens is that when when Vi is low, okay, when Vi is connected to ground, which regions are the transistors in? MP and Mn. What region is MP in? So, V naught will go up to VDD, MP will be in triode. Okay. Now, you can, and nothing, the point is nothing happens to the gate is still drawing 0 current. Okay. If you do this with bipolar, okay, what happens is that this will go up and this will enter the bipolar saturation region, that is a small VEC region. Okay. Once you do that, essentially this base current increases out of control. Okay. So, this is like you are applying VCC across a PN junction. You can't do that, right? The amount of voltage you can apply across a forward bias PN junction is limited, okay, because of the exponential characteristic. If you do try to apply a larger voltage, what happens is the current will go out of control and somehow destroy the device. So, now this is, if you look at this, we had PNP and we have this connected to VCC and this connected to ground. So, across this base emitter junction, you have VCC. Okay. So, that will cause first of all a very large current to flow here and it will also destroy the device. So, you can't use it, you can't use this circuit at all. Okay. So, now I won't show every possible circuit with the PNP. I mean, just like you can convert every NMOS circuit to PMOS by what do you have to do? How do you convert NMOS circuits to PMOS? Reverse you first substitute all NMOS with PMOS and PMOS with NMOS. I mean, that will reverse the polarities of all transistors and you have to reverse the polarities of all sources, independent sources that set the bias. They could be current sources, they could be voltage sources. And then by convention, you draw the circuit upside down. That's all. That's okay. So, I won't show this for every circuit, but I will show one circuit that we have made. That is the differential pair with a current mirror load. It looks exactly like the MOS counterpart. For some reason, the transistors used to be labeled Q, I do not know why. I mean, bipolar transistors. Okay. And then you have VCM plus VD by 2 and VICM minus VD by 2 here. Okay. And this comes from a current mirror. So, this is a single stage op amp and you can also make two stage op amp by following this with a PNP common emitter amplifier. Okay. This is fine. So, this is a two-stage op amp, and just like with the MOS one, you have to stabilize it using a capacitor CC, and you can also have a buffer after this and so on. So, all those circuits are very much possible. Okay. What do you think will be the essential difference between this op amp and the MOS op amp? What's that? Input resistance. Yeah, obviously. In the MOS case, the input resistance was infinite. Now, it will not be. What will it be? The differential input resistance. What I want is the voltage applied across the op amp divided by the current that is drawn from it. How much will that be? R pi by 2. Why? It will be 2 R pi. Okay. So, across this you will have an incremental signal of V d by 2 and here another V d by 2. Okay. So, across R pi you have V d by 2. So, the current drawn from it will be V d by 2 R pi. So, everything else that we did will hold except that the input resistance will be 2 R pi. Okay. In fact, this is a place where you might want to use the Darlington pair or basically another buffer, so that the input resistance is boosted up. Okay. What is the effect of input resistance of the op amp? What happens if the, so let us say loss of signal. So, let us say I have this. And let us assume that the gain of the op amp is quite high. So, we do not have to worry about that factor. So, what will be? First of all, let us assume a MOS op amp with a large gain. What will be V naught? K times Vi. So, now I substitute this with a bipolar transistor op amp. Okay. What will happen? Virtual short is lost. Why? So, essentially that is like, so I will have this right across that. How much current will it draw approximately? What would this voltage be in case of a MOS op amp? What is that? K times Vi divided by A naught, where A naught is the gain of the op amp. Okay. So, now one way of calculating, which is, I mean, you can call cheating or clever approximation, is when you make small changes to the circuit, you assume that this part of the solution has not changed, and then you calculate it, and this is also, I mean, you can call this perturbation expansion or use whatever fancy term you want, but from that you start calculating and then add corrections, successive corrections. So, let us assume that this voltage is the same, about the same as before. Okay. So, what will be this current? If I have 2 R pi over there, what is the current that is drawn from here? KVI by 2 R pi times A naught. Basically, whatever is the input resistance of the op amp, that will appear there. Now, this could still be very small depending on the value of A naught. Okay. So, the input resistance of an op amp is not necessarily a catastrophic thing. It will make a difference because now it will cause some drop. Okay. So, roughly speaking, instead of getting Vi here, what is the value you get? Vi minus Rs by Rin, where Rin for this particular case is 2 R pi times KVI by A naught. Okay. So, depending on the value of A naught, this could still be close to Vi. So, the circuit can still function more or less normally. So, it is not true that the virtual short is lost, because what is the key aspect of the op amp that makes the virtual short possible? infinite gain. Okay. So, that is why you need to have a very large gain. If you do have infinite gain, this is even irrelevant, because the day naught is infinity and there is no difference at all, right. You get all of V I there, but if only A naught is not infinity, it is a bonus to have a large input resistance. Okay. The same for output resistance. I think you must have seen this in one of the previous tutorials, right. Okay. So, we will continue from there tomorrow.